Hey guys.
Yeah, we hear you.
Hello.
Yeah, sorry about that, guys.
That thing.
It's all right.
Just having some serious internet problems. Anywho, let's anyway, that was just sort of on a rant about Kirchhoff's voltage laws, so it's probably not that interesting. But anyway, be that as it may, let's jump in. So first thing I was gonna do is to let's see, just give me 1 second to get my act together. Okay, so now let's jump into what we're going to talk about today. Let's see, I wanted to Okay, everybody still with me, guys?
Yes.
Okay, great. So let's jump in here. So the first thing I was gonna do is to go over quiz 0 with you guys. Just, as I mentioned, it's in the text, but like just sort of go through it and see if you guys have any questions, etc. So let's go through it real quick. So problem 1 was had a input voltage, and there was a resistor called R sub pi here, and a voltage called V sub pi around that resistor. And this was connected to a current source. And the value of the current source was a let me draw this. Okay, so this was the circuit. And it turns out that this is, it's not some accidental circuit they threw in here, but you'll see this when we start talking about transistor. This circuit is an amplifier, and this is kind of what a model for a transistor looks like. But that's getting ahead of ourselves. But that's the reason why this particular circuit was chosen. And this current source is something called a voltage dependent current source, meaning that if you had just a current source, it would always have the same current. Like it would always have this current, it'd just be no matter what, it would be that. This particular current source, the current is a function of another voltage. And this G sub M, which you'll become painfully familiar with later, is the proportionality constant, I guess the way you look at it. Okay, so anyhow, so that's the background for this circuit. So you basically start by doing Kirchhoff's voltage law in this loop to get a relationship. So let me take a step back. Sorry. So the question is, what is V out versus V in? Okay, V out is here, V in is here, and we said we're going to call that something called gain, which is V out versus V in. Okay. So what you'd really like is to put everything in terms of these parameters, R sub pi, G sub M, R sub L, and so that's how you're going to go design it. So the first thing you do is you could go either way, but the first thing I did was to do Kirchhoff's voltage law around this node. Notice that So let me take another step back, which is that Kirchhoff's voltage law says that if you have a bunch of voltage sources, I'm sorry, guys, a bunch of voltage sources. Sorry, guys, this is just getting ridiculous. I don't even know how to stop it. Sorry, that's my Instacart is going off here. So V2 plus and minus V3. So V3. So what Kirchhoff's voltage law says, if I add all these voltages together, that means I go around this loop, then all these voltages have to go back to being zero, which kind of makes sense because if you start from here and you add a voltage, and you add another voltage, add another voltage, add another voltage, by the time you come back, you better be at the same value, okay? So if you look at it in the context of just this thing here, so what we're saying is Vn plus, this guy has to equal to zero because it's a loop. Now the only thing is this V sub pi, look at how it's defined. There's a positive and a negative sort of node around this V sub pi, okay? So that means that you're talking about plus minus V sub pi because it's connected. See, the plus is on this side, minus is on that side. Whereas, when we draw Kirchhoff's equations, it's sort of like more minus on this side, same side as V sub 1. So you have to invert this V sub pi. So this is equal to 0, or V sub in is equal to V sub pi. Okay, so if I rewrite the equation there. Okay, so that's the first thing we have. Okay, you could almost see it by, basically in this case, sort of by inspection, but they can get a little tricky because, by inspection, sometimes you have a tendency to go wrong. So, okay, so that was the V is equal to V sub pi with KVL. Second thing you want to do is Kirchhoff's current law in this particular node here, which is the output node. Okay, so what Kirchhoff's current law says is if you have a node, so let's say this is the node, and I have a bunch of currents going into here. Okay. Then the sum of all these currents has to equal to 0. Okay, so here's our node. Okay, we have one current, which is this guy, going this way. Okay, it's going this way. And then we have another current because we have a resistor going this way, right? So the sum of those two currents have to equal to 0 because they're all coming from the same node. Okay, so this current's pretty easy. It's just GM times V sub pi. So first piece is GM times V sub pi plus this current, okay, is just the output voltage divided by this R sub L. Okay, that's the current by definition going through that resistor. So that's V out over R sub L. Okay, so the sum of those two have to equal to 0. Okay, so if I rewrite this just as a function of, again, remember we're looking for V out over V in. Okay, so here we have an equation for V out. So let's see what that looks like. So, well, let me take a step back. So we want V out and V in. We just said that V in is equal to V sub pi. So we can just plug that in here. So GM V in plus V out over R sub L is equal to 0. Okay, we basically take it to the other side. Okay, and then we rejig it and we end up with V out over V in is equal to minus G sub M R sub L. And that's the answer. Any questions about that, guys? No? Okay. Can anybody hear my dog snoring? No?
Very
Yes.
much, yes.
I do.
Yes.
Oh, yeah.
Sorry, guys. She is not to be denied. She's not to be denied her sofa. Next time I'll sit far from her. Sorry, guys. Hopefully I won't put any of you guys to sleep. I don't want to make her up. All right. Okay, so that was one. So we got problem 2. Okay, problem 2. So we had, again, trust me, this will become familiar to you guys later on. R sub pi. Then we had our G sub M, our voltage controlled current source. Here, this guy is grounded. R sub E, and then this is V sub out. Okay, and we're asking for the same thing, V out over V in. Okay, so the first thing to do is, again, Kirchhoff's voltage law, and both of these are ground, means they're connected together. That means we could do a Kirchhoff's voltage law around this node, essentially, okay? V in, V sub pi, and V out, okay? So if I was gonna write that out, so KVL for that node would be V in plus, notice again, V sub pi, it's, the opposite polarity, so we gotta use it. So we gotta call it a negative voltage, minus V sub pi, okay? And then V sub out is also plus minus here, which is the opposite polarity to V in. So that's also got to be minus V sub out. So all that is equal to 0, or V in is, or remember we want to, well, you can do whatever you want with it, leave it there, or what I did was just said, okay, V pi is equal to V in minus V out. Okay, which again is like, by inspection, you can kind of see it. You got V in over here, V out over here. So V sub pi must be V in minus V out. But it doesn't, I think it's wise at this point to get practice with KVL and all that stuff. Okay, then we can do, again, Kirchhoff's current laws, but we would end up doing it at this node, okay? So Kirchhoff's current law ends up being, so what are all the currents we have? So we have a current coming through here. Let's call that the current from R sub pi. Then we have another current here, which is just GM V sub pi. And then we have a current leaving this node, which is, let's call that I R sub E. Okay, so all those have to equal to, so that basically we're saying this these two are going into here and this one is coming out. So basically these two has to equal to this for the sum of all of them to be 0 at that node. Okay, so first, so I R sub pi plus G sub M V sub pi is equal to IRE. Okay. So at R sub pi, okay, is V sub pi over R sub pi. Just sort of a definition of a current. Is the voltage across the resistor, the resistance. So we have this from this previous equation. So V sub pi is V in minus V out over R sub pi. Okay, so that's the first one. The second one is just, so that was this guy. Whoops. That one was this guy. Second one is just this GM V sub pi. And there's just, again, V sub pi is V in minus V out. So it's GM V in minus V out. And lastly, we have I sub RE, okay, which is this guy here. And that's just V out over R sub E. Okay, so we can throw that all this stuff back into this equation. Okay, so we get I sub R pi, so we get V in minus V out over R sub pi plus GM V in minus V out is equal to V out over R sub E. Okay, and then the rest of this is just sort of separating these things out. Again, we want to get V out over V in. And, you know, basically we have everything we need to just need to solve this equation. So let's say we just put the V outs. If I put everything that has V out on this side, we have 1 over R sub E, which comes from this guy. We have this guy that turns positive and I move it over here, plus 1 over R sub pi. Plus we have this guy, which again becomes positive once it goes to the other side. So that's G sub M is equal to, now on this side we have this and this. So we get 1 over, so sorry, you end up with V in 1 over R sub pi G sub M. Okay, so we end up with V out over V in 1 over R sub pi plus G sub M over 1 over R sub E plus 1 over R sub pi plus G sub M. And then you can sort of multiply it out and you basically get it, or you can just leave it like that for the problem. Any questions, guys?
I had a question about future quizzes, not necessarily this one.
Yeah.
You mentioned that like we need to include the units of measurement. Is that for every step along the way or just in the final answer?
In the final answer. I would, you know, if I were you guys, I mean, in this particular case, we're dealing with variables, so we don't have to do it. My experience is it helps to keep carrying you along every step of the way, because it's sort of another check for yourself to see if you did something wrong. But for the purpose of grading, you just needed to put it at the end.
Professor? Professor?
Yeah.
I was just wondering, so I didn't know about that, but like, you know, you were using KVL on the second part. like, isn't it supposed to be a loop for that to work? Or
I'm sorry, can you say that again?
like for this part, you use KVL on like B in and then all the way down like that. Yeah, I was just wondering, since it's not a loop, how come you're able to use it?
Okay, so the thing is, this is the tricky part, is it is a loop because this is a ground, this is a ground, this is a ground, this is a ground. That means they're all connected together. So when you see a ground here and a ground here, it means these points are connected together.
So then, in that case, if they're all connected, does that mean you can technically do a loop for the entire thing too? Or it just doesn't work that way?
I guess you could. I mean, this one, there's no loop here because this is just sort of, this guy's not, there's nothing going on there. I guess you could have put a loop here, but I don't think it would do anything for you. But you could technically go do this crazy business. Well, I don't know if it would work because it's you could do this, and then you could do this, but then because this is a current source, it really sort of doesn't make sense to put a sort of do a KVL around that, across that.
Gotcha. Okay, okay. Yeah, so basically all the grounds are connected. That's like the main thing. All right, thank you.
Okay. Anything else, guys? Okay. If not, let's just jump into the lecture. But before I do that, let me just say one more thing about the idea behind microelectronics. Okay, what you guys are probably familiar with is, say, things like resistors, okay, or capacitors, maybe inductors, those kind of things. Okay, so let's look at a resistor, these type of circuits that you guys are familiar with. Okay, let's look at a resistor. These are all linear circuits. What does that mean? Let's look at a resistor. There's an equation for, so if you take a resistor and you put a voltage across it, you're gonna get a current. And if I was gonna plot that, so if I put voltage here, current here, I would get a slope. And from this equation, V is equal to IR, or I is equal to V over R, right? So I'm plotting I here as a function of, I'm plotting I as a function of voltage. And so I get this line that's whose slope is 1 over R, just coming from this definition of this equation. Okay, so no matter what I do, if I go forward, I go backwards, no matter what, this is, it's a linear relationship. So there's a linear relationship also between the capacitor, the voltage, and the charge across the capacitor, but it's also a linear relationship. So this is Q is equal to CV. So if you want to plot the charge across the capacitor, it depends on the voltage, and you go back and forth, etc. It's all linear. And inductor voltage is L, sort of the change in current with the time. Again, if the current's flowing forward versus backward, it's a linear thing, meaning that there's a line, and whether you go forward or you go backward, it doesn't matter. It's, again, linear. So as nice as we think about linear things are, there's only so many things you can do with a linear circuit that are interesting in real life. And like, for example, you guys may want to think about this offline, maybe not, you just take my word for it. With putting these linear circuits together, there is no way to get gain. There's no way to make the output be higher than the input. Okay, and there's no way to get a switching circuit out of this either. And if you guys remember going back to the first lecture, switching circuits were what we use for logic gates, which sort of makes the world go around. Okay, so what we'll be looking at, the type of circuits we'll be looking at in this class, specifically when we first start in chapter 2, is something called a diode. So I'm just kind of giving you a heads up about what we're going to discuss. And that's a nonlinear circuit. That means if I do the same thing for a diode, if I plot the voltage versus current, okay, they'll end up looking something like this. End up looking something like this. Okay, very nonlinear circuit. It's doing, there'll be something you'll see, it'll be called the threshold voltage or diode voltage or whatever. And you know, the diode will have a very low resistance past that point. And remember this, the slope of this curve is always 1 over R, meaning that here the diode has a very low resistance because the slope is kind of close to being infinite. And then here it has a very high resistance. And it turns out, as we'll see, there's like lots of useful features that this nonlinearity gets you. And then we'll talk about transistors, et cetera, and you'll see that again, they're useful features. Okay, so first thing we'll talk about is what this nonlinear circuit elements are made out of. They're made out of these things called semiconductors, okay, which again, we're gonna have to talk about a little bit. And so first we'll talk about what this material is. We're gonna go through that super fast. You can get, you know, I got my PhD for the most part in sort of semiconductors. You could spend years talking about it, dissecting it. We're just gonna go over it real fast in an attempt to get to PN junctions, which are, you know, which are also known as diodes, which is the circuit element I just talked about that has this nonlinear characteristic, okay, which will be useful. So anyway, will be steps we talk about what charges are and how we can modify them and etc. So let's first talk about what this stuff is made out of, and just to begin with. Okay, so you guys, I'm sure everybody's heard about silicon chips, Silicon Valley, etc. Well, it's an element in the periodic table. Okay, it's a group 4 element in the periodic table. And it was kind of, I guess, I don't know if it was lucky or great science that humankind has found this material. And one of the nice things about this silicon and the fact that it's a group 4 element is that you can modify its resistance by adding or subtracting things from group 3 or group 5 in the periodic table to it. Okay, so let's look at what it means for something to be a group 4 element. So a group 4 element, okay, means that this atom of silicon has 4. So 1, 2, 3, 4 valence electrons. Okay, what's a valence electron? It's an electron that's in the outer shell of the atom, and it's what sort of bonds to the other atoms around this particular atom with these valence electrons. So if you had a bunch of silicon atoms next to each other, they would all be connected to each other using these covalent bonds. Okay, so a silicon atom has 4 covalent bonds. It means that it can connect up to another 4 silicon atoms around it. And this is in a sort of what you'd call a crystal lattice. Okay, so if you held this in your hand, it would just sort of feel like a really polished rock or something, right? So it's a piece of solid. So as silicon is solid at room temperature, and so it'll just be a bunch of silicon atoms sitting next to each other, each one of them having 4 covalent bonds with the atoms next to each other. Okay, so it turns out that that's just, you know, a material with 4 covalent bonds. It turns out that you know, when we're talking about so far, what you've heard about probably or seen in circuit classes are insulators. That's what capacitors are made out of. So you have a node in a capacitor here, a node here. There's like basically infinite, there's no current flowing from the plus node to the minus node of this capacitor. So there's an insulator in between. So insulators do not conduct at all. Okay. On the other hand, when you have, say, a resistor, always when you have voltage across a resistor, you get a current. So that the resistor is made out of a conductor. And these always conduct current. Okay. So what we're talking about now should be giving you a clue as to what these things do. It's called a semiconductor. And this means that it sort of conducts under certain circumstances. Okay, so what are those circumstances? When you look at this node, this case, you don't have any conduction here, right? There's nothing to conduct. There's all the electrons. Remember, conduction happens with electrons. An insulator has no free electrons in it. A conductor has like an ocean of free electrons. And a semiconductor, when all the covalent bonds are taken, there are no electrons. So it's acting like an insulator in that case. Now, fortunately, this is only the case at 0 Kelvin temperature. So that means at minus 300 Celsius when you're very, very cold, low energy. Now, what happens at higher temperatures than that, let's say you're using the silicon at room temperature, and that's defined as 300 degrees Kelvin, okay, or roughly 30 degrees Celsius. Okay, what happens is some of these electrons get energetic enough to break free from these bonds and start floating around the lattice, you know, some of the electrons, not all of them. And you'll see there's an equation for what percentage or what number of electrons do that. But basically, as the temperature increases from 0 degrees Kelvin, we get more and more of these electrons floating around. And by the time you get to the room temperature, which is 300 degrees Kelvin, then you have sort of a significant amount of these electrons, enough that we're going to get some amount of conduction. Okay. So one way a semiconductor starts partially conducting is at higher temperatures. Okay. And as the temperature goes up, let's say this piece of silicon is at 50 degrees Celsius, it'll conduct more. than when it was at 30 degrees Celsius. Okay. So another thing to try to get your head around in a semiconductor is once this electron leaves the covalent band and starts floating around everywhere. Okay. Now my dog is panning, guys. Sorry about it. This is like a lot of distractions in this class. The next classes will be better. Sorry. I'll find another spot for this. So once this electron is floating around, there is an empty spot here where that electron no longer is. So let's say if it was here, this electron left and there's an empty bond there, okay? And just in the semiconductor business, this empty spot where the electron used to be is called a hole. Okay, and then it turns out that because this hole now, it can steal without any of these adjacent electrons becoming free, it can actually switch spaces with this hole. Okay, so the hole can move from here to here, which you'll see here, then it can move here, then it can move here by just these electrons swapping their stuff for this lack of an electron. So this lack of an electron is called a hole. Okay, it's not a positron or something like weird like that. It is just a lack of a covalent electron, an empty spot that can get filled with covalent electrons that don't have to free themselves. Okay, so the upshot of this is this hole, besides the electrons acting to conduct by being free in the lattice, this hole is actually sort of conducting in the lattice too, because this hole, sort of being a lack of an electron, has a positive, so it has the same charge as a positive electron. Okay, so an electron's charge, so charge of an electron is defined as E minus, is minus 1.6 times 10 to the minus 19 coulombs. So it's a negatively charged particle, as you guys know. A hole has the same amount of charge, but it has a positive charge. And basically, this hole can kind of move around as if it was a positively charged electron. So it's also a mobile particle. So the electrons, once the electron flies off, it's a mobile particle that's acting as a conductor or conducting current. And the hole can separately act as an element that's floating around and conducting. Okay, so you have those two. And it turns out there's this equation, okay, for the number of free charge carriers in a semiconductor, which is basically this equation. Okay, so this is the charge density. So Ni is, let's see, Ni is the density of free charge carriers. In this case, electrons, and is usually referred to the electrons. Hole, you'll see it's called P sub I, but anyway, let's focus on the electrons now. So notice that it's per centimeter cubed, this number of electrons per centimeter cubed. And notice that it's a function of temperature in a very strong way. There's to the 3/2 here, which seems like a pretty reasonable dependence on temperature. But notice it's also a function of temperature in an exponential sense here. Okay, so basically you got a very strong function of temperature for these free electrons. Okay, there's a couple of other constants I want you guys to try to, I don't know if you're going to write it down, remember it, whatever, you'll see this over and over again. One of them I already mentioned is the charge of an electron. Okay, it's 1.6 times 10 to the minus 19 coulomb. That'll show up over and over again. The other one that'll show up sometimes is called Boltzmann constant, which is this K here. And this is 1.38 times 10 to the minus 3 joules per coulomb. I never remember that, so I just always have to write it down. And then the second thing that are very dependent on is, this equation is very dependent on, is the band, what's something called the band gap. Okay, so E sub G is the band gap energy. And that's sort of defining for a particular type of material how easy it is for the electrons to go free. Okay, so for example, the band gap for silicon is 1.12 electron volts. Okay, the band gap for something that's a insulator like a diamond is higher than that. So like a diamond is a 2.5 electron volt band gap. And so when you look at a semiconductor, the band gaps are usually from 1 to 1.5 electron volts. But for the most part, for actually entirely for this class, we'll be talking about silicon. So you'll be looking at this band gap 1.12 electron volt. Okay, so exponential relationship. So then we've got a couple of examples here. Sorry, one more thing I wanted to tell you guys. Again, this is all important stuff because you'll see it over and over again in the first part of the class in these equations. Whenever we're talking about room temperature, by definition, it is 300 degrees Kelvin. Okay, so whenever in a problem or whatever you see room temperature, that's what it means is 300 degrees Kelvin. It's just something that, you know, everybody just sort of in electronics, that's what they mentioned. Okay, so at room temperature, if you look at this, there is 1.08 times 10 to the 10th electrons per centimeter cube. That's a density of free electrons in a centimeter cube of silicon at room temperature. So notice when you go up another 300 degrees above room temperature, so at 600 degrees Kelvin, now you end up with 1.54 times 10 to the 15th electrons per centimeter cube, or, you know, it's almost, not quite, almost 5 orders of magnitude higher than at room temperature. So basically you have this exponential relationship between free electron density and sort of band gap energy, and almost that way from a relationship with temperature. Okay, so we saw how temperature affects the density of free carriers in a semiconductor. And remember again, the reason we're interested in free carriers is free carriers basically determine how conductive a piece of semiconductor is. Okay, so the other thing that affects the density of charge carriers in a semiconductor is your structure, your crystalline structure does not have to be all silicon. If somehow you manage to put in some other type of atoms that were different than silicon, you could still affect these density of these charge carriers. So how does that work? Let's look at phosphorus. Okay, so phosphorus is sitting in, it's a group 5. Okay, it means that it has, so this group 4 has 4 valence electrons. Group 5 has 5 valence electrons. That means that if you had a phosphorus in a lattice of silicon, regardless of what temperature you're at, you always have an extra valence electron just floating around, and it's not being, it's not being constrained or held down by being connected to something around it. So just because phosphorus has 5 valence electrons means that you'll end up with extra electrons. So if we could add phosphorus to silicon, and that process is called doping. Okay, doping means somehow you managed to add some number of different atoms to your semiconductor. So as you add these phosphorus atoms, you end up with these extra electrons regardless of temperature. So it's a way, if you can put these dopants in, it's a way to get extra electrons built into your material. Okay, so that's this first approach. And then you could do the reverse. If you had, we said phosphorus is a group 5 element. Okay, so it has 5 valence electrons. So you'll end up with an extra, an excess of electrons. And we said, like, what if we use a group 3 element? So that is called, let's say we pick boron, for example. Now this one has 3 valence electrons. Okay, so what happens there? You end up with an empty, if it's sitting in with a bunch of silicon atoms, the boron has only 3 valence electrons, means that one connection will be lacking an electron, or you'll end up with this hole. Again, regardless of an electron going free because of temperature, regardless, you end up with this hole anyway. So if you want more electrons in your semiconductor, you dope the semiconductor with a group 5 element. Phosphorus is very popular for that. And if you want more holes, you dope the semiconductor with a group 3 element. And again, boron happens to be popular for that. Okay, so this is kind of like summarizing what we just talked about. So basically, you can get more holes or more electrons. Okay, another thing that we're not gonna, this is a very, very important equation that we are not gonna be proving or anything in this class, is that if you have, so n sub I is, we defined it here. This is the electron density without any dopants added to the material, okay? So basically the equation is that in any semiconductor, if you multiply the number of electrons by the number of holes, it's equal to the density of the intrinsic density of electrons squared. This is always the case. So you're just going to have to take that on faith and remember that equation, that n times n is the density of free electrons. P is the density of holes. And n sub I is that equation, is the density of free electrons in intrinsic silicon. I mean, just instead of intrinsic, well, intrinsic, let's call it intrinsic. No, I'm not calling it. It is called intrinsic, which means not doped. Okay, so this is a set equation. Okay, so let's say we dope, we have a piece of silicon, and we put a bunch of boron in here, a bunch of group 3 elements. Okay, so we end up with a bunch of extra holes. Okay, what happens is that we can put in so many extra boron atoms here that we can basically get a higher density of holes than the intrinsic density of electrons. So that means the number of holes in that case ends up being equal to the density of acceptor atoms that we dope the silicon with. So n sub A is the density of group 3 elements added to the silicon. Okay, and the reason that there's like all these verbiage that people have around semiconductors. So group 3 elements are called acceptors. Okay, so this is n sub A. A stands for acceptor. Okay, and so if we say that, if we put in so much that the density, if you put so many of these boron atoms, for example, that we just much higher than the intrinsic density, we can by design make the number of holes in there equal to just the density of acceptors. So for example, remember that in room temperature, the intrinsic density of electrons was 1.08 times 10 to the 10th electrons per centimeter cubed. Oops. And so let's say, we go in and insert a bunch of boron atoms into this silicon. And let's say, I can put in as many as I want. I mean, imagine this isn't actually 1.08 times 10 to the 10th per centimeter cube. There's still like a huge amount of silicon atoms more than that. So I could put in, if I wanted to, I could put in, say, I don't know, 1 times 10 to the 12th boron atoms per centimeter cubed in this same semiconductor. If I could, and I can insert these in there, then basically the number of holes, notice the number of holes would be equal to this, which is 2 orders of magnitude more than that. So I could just say the number of holes is equal to the density of these acceptors in that case. Okay. So now, because of this first equation that we have here, okay, because of that equation, so we say that n times p is equal to ni squared. We said that we put in so many acceptors that p is equal to the density of acceptors. So n times, basically this becomes n times n sub a is ni squared. So the number of electrons ends up being ni squared over n sub a. Okay, so that you can see that when we put in a lot of acceptors in a piece of silicon, so that the density there ends up being much higher than the intrinsic carrier density. The other type of material, so that means holes in this case, right? Acceptors means you get a lot of extra holes. And what it leads to is you end up with having much smaller number of electrons. So because this is already, 1 point, so let's throw in some numbers. Okay, in this case, we said n sub a is 1 times 10 to the 12th per centimeter cubed. Okay, we said n sub I is 1.08 times 10 to the 10th per centimeter cubed. So in this case, n sub I squared is just about approximately 1 times 10 to the 20, okay, per centimeter to the 6th. So n ends up being 1 times 10 to the 20 over 1 times 10 to the 12th per centimeter cubed. It ends up being 1 times 10 to the 8th per centimeter cubed. Okay, so now notice this thing, this really lopsided density now. So we said that the number of, well, so this is n, 1 times 10 to the 8th per centimeter cubed. P, which is equal to this Na, is 1 times 10 to the 12th per centimeter cubed. So in this case, by adding these boron atoms, we made the density of these holes 4 orders of magnitude higher than the density of electrons. Okay, so you can quickly basically create an imbalance by adding these extra atoms. You can create an imbalance between the density of electrons and holes, and like a significant imbalance. Okay, and you can do it the other way too. If you added a bunch of phosphorus, for example, so those are called donors, and those are group 5 elements. You end up getting like a nexus of electrons, and you drive down the number of holes. So basically, you have these concepts called majority and minority carriers. And majority carrier is whichever carrier is you have an excess of. So if you dope a semiconductor with group 3 elements, which are also called acceptors, if you dope it with that, the majority carriers are going to be holes. And the minority carriers end up being the electrons. Or if you dope it with group 5 elements, which are also called donors, you end up with an excess of electrons and a minority of holes. And so your majority carriers become electrons, minority carriers become holes. Okay, so those are our definitions. So I'm going to stop there, guys, for today, because those are all the definitions that we talked about what a semiconductor looks like, how you can change the number of free carriers, which are gonna basically are responsible for your conduction. And then on Thursday, we're gonna talk about what the different conduction mechanisms are once you have those electrons and holes in your system. Okay, guys, any other questions? Any questions, I should say?
Is silicone the only, I mean, it's not the only semiconductor that they use, right? It's just the most popular one.
Yeah. So, the other ones that, you typically see are germanium. You see gallium arsenide. And you see gallium nitride. There's a few other ones, but, by far, and I don't know what the ratio is. Like it might be by billions to one. Like silicon is by far the most used semiconductor. So
Is that maybe because of cost?
it comes from cost, but there's something that we'll see later in the class, and it turns out that I think I mentioned, if you remember from the first class, that most of the semiconductor chips in our systems are using this thing called the MOS transistor.
Mm-hmm.
So, all the chips in your iPhone, whatever, are using this MOS transistor. And a very important part of this MOS transistor is its metal, MOS stands for metal oxide semiconductor. So it turns out an important part of this transistor is this oxide. And it turns out that silicon has a very well-behaved oxide called silicon dioxide that makes a very, very clean interface for making these transistors. So that is not the case for any of these other semiconductors. So people have been looking for another semiconductor that has such a nice oxide to be able to get a MOS transistor. MOS transistors are nice for making digital circuits. By nice, I mean they are absolutely necessary. So that's a big part of it, is that it has this nice, not just the silicon itself, but also the oxide part of this silicon is very important. The fact that exists.
I see.
Yeah, and that's led to it being used for digital circuits, and that every time it gets used for digital circuits, they sell a lot of it, and it gets cheaper. Then they make more of it, gets cheaper. More research money goes into it, gets cheaper. So you're right. Basically, the fact, but the initial fact that it's a very nice silicon oxide combination allowed it to get this traction and sort of get very, very popular. So the other stuff like gallium nitride, I just bought a wall charger for my iPad. The only reason I bought it was because they claimed it has a gallium nitride chip. It's getting used for sort of high voltage circuits. So it might become more popular, but it's not going to get anywhere as close to popular as silicon. Germanium, you'll see it in some of the diodes, like light emitting diodes, like LEDs, will be germanium. Gallium arsenide is used in some detectors in the infrared. It's also used for some parts of the radio frequency circuits, like just some specific chips. But again, all these are sort of really very much in the exotic camp. Silicon is like much more powerful. I mean, much more widely used. Any other questions?
Thank you.
Sure. Any other questions?
I have another off-topic question, but I'll wait till later, or I'll probably just email you,
Okay.
whatever you prefer.
Email might be best, just because I might have to, I'm gonna have to prep for my other class here coming up in a few minutes.
Okay.
Great, thanks. Okay, guys, if there aren't any other questions, I'll close it here and I'll see you guys on, or talk to you guys on Thursday. Take care.
All right. Thank you.
Thank you,
Professor.
Professor.
Thank you,
Thank you.
Professor.
Thank you.